In today's lesson, we are going to look at the sum of interior angles. First, we're going to do a little bit of investigation looking at the different polygons and what the sum of their interior angles could be. So let's start with one of the easiest shapes, the triangle. We've already looked at the sum of angles inside a triangle, but let's take a look at it just to help us get started. So we have a triangle or a polygon with three sides. The number of triangles that we can make basically by picking a vertex and drawing a line to another vertex, right? So I can't really do that here because these are the only lines that I could draw and doesn't make any changes. But we can see that there is only one triangle because this shape is a triangle. And we know the sum of interior angles is 180 degrees. Now let's take a look at a square. Again, we've already looked at a square, so we should be familiar with this one. We could probably already just fill out the sum of interior angles, but let's go through these steps anyways. So I'm going to pick a vertex, and I want to draw a line to another vertex. So I'm going to draw one right across there. Now, I can't draw a line to any other vertex. Right? I could draw one here, that doesn't do anything. I could draw one here, that doesn't do anything. It doesn't split up my shape. Right? So I want to be able to draw it to other vertices. And I'm only using one, so I'm not picking another one over here and going like this. Right? We're only picking one vertex to draw our lines from. Here, we can see that this is a four-sided figure or a square. Now, how many triangles do we see after we've kind of drawn these vertices or these lines? Right, and we should see 1 and 2. So there's two triangles in this shape now. So there's two triangles, and we know from before that the sum of interior angles of a square or a four-sided figure is 360 degrees. Let's move on to a pentagon. It's a five-sided figure. I'm going to pick a vertex. I'm going to draw lines to other vertices without kind of touching other lines. Right, so I can draw one here. I can draw one here. Right, I'm drawing straight lines. Now, how many triangles are there in this shape? Well, taking a look at based on the lines I've drawn, there's 1, 2, 3 triangles. So 3 triangles. Now we don't really know how many or the sum of interior angles in a pentagon, but let's kind of reason through. If each triangle has a sum of 180 degrees, what would 3 triangles have? Well, 3 times 180 is 540. If I know that there are 3 triangles in there, or if I know how many triangles there are in our polygon, I should be able to figure out the sum of interior angles. Let's try another one. Let's try a hexagon, a 6-sided figure. So I'm going to pick one point. I'm going to draw lines to other vertices. So there, I've drawn them all. So it's a 6-sided figure. Let's count how many triangles there are now. 3 and 4. So there are 4 triangles. Make it a little bit bigger. So 4 times 180 is 720 degrees. Moving on to a heptagon, a 7-sided figure. Right, again, picking a vertex, drawing lines to other vertices. I have 1, 2, 3, 4, 5 triangles. So I have 5 triangles. So if each triangle is 180 degrees, 5 times 180, I get 900 degrees. I want you to go through the last two. I believe it's an octagon, and then we got 1, 2, 3, 4, 5, 6, 7, 8, 9, an octagon, and then a nonagon. And I want you to try to come up then with a rule for any number of sides. So take a second to try these two, and we'll come back with the answer. So coming back to our octagon and our nonagon, we should get that in our octagon, our 8-sided figure, we have 6 triangles, which would give us a sum of 1080 degrees. And in our nonagon, we would have 9 sides, which gives us 7 triangles. Oops, I've written 8. 1, 2, 3, 4, 5, 6, 7, 8. Maybe this is not a nonagon. 1, 2, 3, 4, 6, 7, 8, 9, 10. That is not a nonagon. That is a decagon. My mistake. So it is a decagon, and there are 8 triangles. So if there are 8 triangles, that gives me 1,440 degrees. So I could use this kind of idea. If I was given any shape, I could pick a vertex and draw lines to other vertices and create triangles and then count how many triangles there are. But is there a relationship between the number of sides in a figure or in a polygon and the number of triangles? So looking at our 2 middle columns, do we notice anything about those numbers? And what we should see is that based on the number of sides, or n, the number of triangles is always going to be n minus 2. So if I have 10 sides, I have 8 triangles. 8 sides, 6 triangles, and so on. And if I know how many triangles there are, how do I find the sum of interior angles? Well, if I know each triangle is 180 degrees, I just need to do 180 times the number of triangles, which is n minus 2. So this formula here will give me the sum of interior angles for any sided polygon, with n just being the number of sides. So now let's use that to kind of look at some relationships between angles and polygons. Right, so we just mentioned the sum of interior angles in a polygon with n sides is 180 times n minus 2. The sum of exterior angles of a polygon with n sides, and this one we didn't look at, but we did look at this in some previous ones, and we did find that it was always going to be 360 degrees. So it doesn't matter how many sides a polygon has, the exterior angles are always going to add up to 360. Now you might see the term regular being used with angles or polygons, and a polygon is called regular if the side lengths are equal and the angles are equal. Right, so this might be something like a square or an equilateral triangle. Right, so we do have some different names for a quadrilateral that's regular, which is a square, or a triangle that's regular, which is an equilateral triangle. We don't sometimes have those terms for other sided shapes, so we just call them regular. So if they're regular, the side lengths are equal and the angles are equal. So in example 1, let's determine the sum of interior angles in a regular nonagon. So nonagon means 9 sides. Right, we want to find the sum of interior angles. Right, because it's regular, all of these angles are all equal. So we have our formula. S is equal to 180 times n minus 2. So 180 times 9 minus 2, or 180 times 7, gives us 1260 degrees. So that means in this regular 9-sided polygon, all the angles are going to add up to 1260 degrees. Now the next step is, what is the measure of an interior angle? So I want to know, what is each angle actually measured at? Well, I do know that the sum is 1260 degrees. And if I'm going to divide that up into 9 angles, right? Because if I have 9 sides, I also have 9 angles. So I'm going to take that sum, divide it by 9, because it's a regular, all the angles are the same, and I get 1040. So that means, or sorry, not 1000, 140. So that means each angle is 140 degrees. Example 2, now we're trying to look for the sum of exterior angles. So I want to know, what are all of these angles adding up to? What do all those exterior angles add up to? Well, we had that property, the sum of exterior angles in any polygon is 360 degrees. B is now asking, what is the measure of an exterior angle? Right, so what is this measure? Right, or all of these measures. Well, I know the sum is going to be 360 degrees. So because it's a regular pentagon, oops, I forgot the N here. Because it's a regular pentagon, all these sides are the same. All these interior angles are the same. So all the exterior angles have to be the same as well. So I'm going to take 360, divide it by 5, and get 72 degrees. So that means each of these angles is 72 degrees. Lastly, the sum of interior angles of a regular polygon is 1,800 degrees. And I want to determine now the number of sides this polygon has. So what I'm going to do, right, I'm going to start with my formula. S equals 180 times n minus 2. Now in this case, I am already given the sum. Right, so that's already given to me. So I'm going to plug that into my equation. So 1800 is equal to 180 times n minus 2. And now I can actually solve this equation for n. I'm going to divide out the 1800, or the 180. One side will cancel out. I'm left with 10 is equal to n minus 2. I'm going to add 2 to both sides. One side will cancel out. I get 12 is equal to n. So therefore, the polygon has 12 sides. And if we're not sure what a 12-sided polygon is called, there is this kind of like flowchart idea of how we could name it. Right? We do have some of the ones from 3 to 10 kind of already listed, and if we just want to kind of have the quick way, we just take our prefix and we just add gon to it. So 12-sided dodecagon is a 12-sided polygon. Right? If we wanted to look at some other ones, there are some kind of different constructs, right? So if I could start with the tens prefix, so say I wanted to do 21, right? A 21-sided polygon. So I'd start with ICOSI, ICOSI, or ISOSI, followed by chi, because that will tell us, so 20 and 1, so ISOSI chi hinagon would be an example for a 21-sided figure. Right? Now there are some kind of shortcuts. Right? We look at some kind of like the pentadecagon, hexadecagon, right? There are some kind of shortcuts to some of these, some of the more common ones that we use. But for some of the more uncommon ones, it's kind of like we have these kind of more step-by-step way of naming these polygons. So just if you want for fun, try to come up with a different name, or try to come up with a name for an unknown sided figure, or an odd sided figure, and see if you can get your friends to guess how many sides the polygon has based off of the Greek name.